Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe.
Hello future engineers, welcome to my YouTube channel. If you're still new to my channel, please don't forget to subscribe and press the notification bell so that you will be updated of my future videos. I hope that these lecture videos that I uploaded in YouTube will help you a lot in your different subjects in engineering. And most importantly, please continue to support my channel, and I hope that you also enjoy watching my videos. So good luck in your studies. So let's have first the fundamentals of statics, or in particular mechanics. So first, let's define some terminologies here. First, statics of rigid bodies is a branch of physics that deals with the study of forces and their effects to rigid bodies. Rigid body is a certain amount of matter, every element of which is fixed in position relative to the surrounding neighboring elements. So that's the definition of a rigid body in statics. So when you say rigid, strictly all neighboring elements should be fixed in position relative to the surrounding neighboring elements. So strictly speaking, there's no such thing as rigid body, but in statics, all bodies that are considered solids, as long as the resulting deformation due to the effects of forces will be negligible compared to the size of the body, then those bodies are considered rigid. So a particle is a certain amount of matter with considerable mass or weight, but of negligible size. So you are considered a particle relative to your path. The car is considered a particle. That's a very small object compared to its path also. The Earth, which revolves and it traces its orbit, can be considered a particle relative to its orbit. So that's the definition of a particle. A mass is an absolute property of matter that determines its resistance to translational motion. So that's the definition of a mass. The greater is the mass, the greater its resistance to motion. So just consider a body of mass very small, and if you throw that mass upon a very large body of higher mass, then that body may move a little or it may not move because the body has a very high mass. Weight is related to the amount of force that acts on a body, either due to gravity or to a reaction force that holds it in place. So that's the definition of weight. Then force is any interaction that tends to change the state of motion of a body. So that's a force. So if you apply a force to a certain object, if that force causes the body from rest, then it now moves, then we know that a force is applied. Even if the body does not move or it remains at rest, as long as you apply a force, then as long as there is reaction, it may be due to friction that holds the body to remain in equilibrium, so there is still a force. A force may also be defined as the action or reaction transmitted by one body upon another body in contact with each other. Moment of a force is a vector quantity, which is the product of a force and the perpendicular distance between the line of action of the force and the point on the body about which rotation is possible, or rotation is possible to occur. So for instance, we have here a wrench, and you apply a force, you exert a force through your hand, and the force is directed, let us say, in that direction with a magnitude of F. Then the perpendicular distance of that line of action of force to the point about which rotation is possible, or tends to rotate about this point here, which is a bolt. Then the amount of moment is simply the magnitude of the force and that perpendicular distance from the point where rotation is possible to the line of action of the force. So this distance, perpendicular distance to the force, is called moment arm, and the point on the body about which rotation is possible is called the moment center. So we will call the moment arm as D and the moment center as O. So it has sense. It is either clockwise or counterclockwise for this case, but it is counterclockwise that is positive in statics. So when the force is applied, then this moment arm D tends to rotate counterclockwise. So the sense of rotation of the force is the tendency of this moment arm to rotate about this point O here, moment center. So if this moment arm tends to rotate counterclockwise, then the sense is counterclockwise. If it is clockwise, then it is clockwise also. So when force F is applied, then this moment arm D tends to rotate counterclockwise. So that's why the sense of moment is counterclockwise. And that's the positive rotation in statics, just like the measurement of angle in trigonometry, counterclockwise is positive. So point O again, or any point about which rotation of the moment arm tends to occur, is called moment center. Then vectors are types of quantities that possess both magnitude and direction. So therefore, they are added geometrically by means of the parallelogram law or the triangle law. In mechanics, vectors are forces, couples or moments, momenta, impulses, torques, velocities, acceleration, and displacements. Vectors may also be fixed vector. Magnitude, direction, and point of application are fixed. Sliding vector, magnitude and direction as well as line of action are fixed. And sliding or free vectors, neither point of application nor line of action are fixed. So those are the definition of vectors. Scalars are types of quantities that possess magnitude only, and therefore they can be added arithmetically. Examples of scalars are times, temperatures, speeds, distances, areas, lengths, volumes, energies, masses, and second moment of a mass or the moment of inertia. All of these quantities can be added arithmetically. So they are scalars. Then resultant is the simplest force system that is equivalent to the original system. Equivalent to the original system or equivalent to the effect of the original system. The simplest force system is called resultant. Equilibrant is a force system that counters the resultant so that the system will be in equilibrium. So that's the definition of equilibrant. Then characteristics of a force. The characteristics of a force are its magnitude, which may be Newton, kilonewton, pounds, dynes, point of application, and line of action. So those are the characteristics of a force. The external effect of a force to a body is manifested by its tendency to change the state of motion of a body. So as before, if the body remains at rest, due to its own weight and other action forces, it means it is held in equilibrium by the reaction forces. The internal effect of a force to a body is manifested by producing stresses and deformations. So that's it. And these are not seen externally because we have to investigate the body internally, and we have to compute for these stresses and deformations. Then let's proceed to axioms of mechanics. These are statements that are assumed to be correct without proof, and this must be based on your experience from your statics class. So the parallelogram law, which states that the resultant of two forces is the main diagonal of the parallelogram formed on the vectors of these two forces. So the resultant is the main diagonal formed on the vectors of the two forces. The main diagonal may not be the longest diagonal of a parallelogram. All you have to do is arrange so that that main diagonal or the resultant is obtained by making a parallelogram. So from the two forces, you draw a parallelogram. Then the main diagonal is defined as the diagonal drawn from the tail of the two forces, then to the tips of the free vectors of the forces. So if this is F1, that is F2, this is the common tail of the two forces, then you draw lines parallel to these two forces here to make a parallelogram. Then the main diagonal here would be from this tail to the opposite corner of the parallelogram. So that's the resultant, and that is F1 plus F2. Take note, these are vectors, boldface, so it's not F1 plus F2. This is to be computed geometrically by means of this parallelogram or by means of this triangle. Then for the triangle, you have to draw the first force, then connect the second force. The order of the arrangement of forces is irrelevant. So meaning to say, it is in any order. So for example, if you begin with F2, then you connect F1, then the resultant is the diagonal or the third vector, which is formed from the tail of F2 to the tip of the second force, which is F1. Or you begin drawing F1, then connect from the tip of F1, F2, then the resultant is that the vector that is drawn from the tail of F1 to the tip of F2. So which is the same. So that is F1 plus F2. So the question is, if the main diagonal of the parallelogram is the geometric sum of the two forces, what does the other diagonal represent? So the answer is it's the difference of the two forces. So if this is F1, that is F2, take note that the negative of F2 is the same vector except that it is directed opposite to F2. So this is the negative of F2, and if we form a parallelogram again, then this diagonal from the tails of the two forces to the opposite corner of this parallelogram is simply F1 plus negative of F2. So the arrow is from the tail to this tip, but if the arrow is from this tip to the tail, then it is the opposite. So it is F2 minus F1. But for this case, it is F1 plus the negative of F2. The next Action is two forces are in equilibrium when equal in magnitude, oppositely directed, and collinear in action. So take note that there are three conditions for two forces to be in equilibrium. They must be equal in magnitude, oppositely directed, and the third, they must be collinear in action. Or else, if they are not collinear in action, that constitute a couples and the body will rotate. So we have here an example. These two forces are in equilibrium because they are equal in magnitude, oppositely directed, and collinear in action. So another example, then the last one is this. So that forces may be removed out of the body because the two forces are in equilibrium. So because of that, any number of sets of equilibrium forces may be added to any four systems without changing the external effect of the original system. So remember here, in this third case, we remove the forces. You can also add them back as long as they are in equilibrium. In fact, you can add any number of pairs of equilibrium forces. The effect to the original body, to the original system, is the same. So it may have free of forces that are in equilibrium, or it may be with so many equilibrium forces applied. Anyway, you can remove those forces, pairs of forces that are in equilibrium. So to illustrate or demonstrate, so we have here an original system that is equivalent to this system here, and if we add two forces in equilibrium, the original effect is not affected by adding these two forces in equilibrium. Or equal to this another set of forces. So we have first pair of equal forces or equilibrium forces, then another pair of equilibrium forces, and so on and so forth. Then the original system, the original effect of this system here is unaffected by the addition of any number of equilibrium forces. And lastly, action and reaction forces are equal but oppositely directed. So the action forces are those that are directly applied to the body, such as its own weight, or the natural forces, such as due to water pressure, wind, the occupants, loads due to the occupants, and earthquakes, like that. So for instance, we have here a body and its weight is W, then the reaction should be equal to and oppositely directed to W. So the resultant is equal to W. The resultant may be represented by another force, or this weight here is transmitted to this horizontal surface, then it may be distributed and the reaction may be in a form of pressure, and the pressure may be uniform or not. So let's assume first that the pressure is uniform of intensity P, so that the resultant is simply pressure times the area, and it should also be equal to the weight W. So that's the fourth axiom of mechanics. And I hope that you recall all these axioms of mechanics because these are very important in the analysis of force systems. So again, the action forces are those that are directly applied to the body, such as the weights of the members and equipment, and external loads caused by the occupants, people, and natural forces such as water pressure, wind, and earthquake. The reaction forces are those that are developed or transmitted forces at the contact points between two or more contacting bodies. So, for example, to demonstrate the action force in this system here that is in equilibrium, so we have bar, and the bar supports this cylindrical body, maybe, and let's assume first that this vertical surface is smooth. Then we have a pin. A pin has two reaction components, horizontal and vertical, because the bar is free to rotate about A. Then we have here a cable or a rope that will produce tensile force. So cable or rope. Then we have a smooth bar or strut. Then we have smooth lug or cylinder. So we have also a smooth wall surface. So if we draw the free body diagram of this entire system, so first we have to apply the action force, which is the weight, and the reaction forces. So if we consider the entire system, then the reaction at D is external because this is an external wall surface. So we have so if you treat this as your body, then you can feel that you are compressed at D. So a compression force is pointing, or it is pointing at the point of contact or towards the body. So at point D, so we have reaction here ND, which is perpendicular to this vertical surface because the surface is smooth. Then we have here the tension in the cable, which is away from the point of application. And of course, at these pins here, we have two reaction components, vertical AV and horizontal AH. Now, the direction of these reaction components, external reaction components, is arbitrary. It's up to you, but you also anticipate the direction. There's no problem if you commit a mistakes with regards to direction, because when you analyze the body, it will just give us a negative value. So if the result is positive, it means that you have correctly directed these reaction components. If negative, it's the opposite. Then of course we have the tension, which is away from the point of application. So to distinguish between compressive force and tensile force, a compressive force is indicated in the free body diagram as an arrow with the head pointing towards the point of application. So this is, for instance, a compressive force. We have a point, it is directed towards the point of application. A tension force, on the other hand, is indicated in the free body diagram as an arrow with the head pointing away from the point of application. So example, this is the point, so the tension force is away from the point of application. The free body diagram, where FBD is a portion of a body or the whole portion of contacting bodies, showing the action and the reaction forces, and of course with the dimensions, completely labeled with dimensions, and the details needed for the complete analysis of that body or system. So if we want to draw the free body diagram of the cylinder of that smooth lug, so first we have the action force, the weight, then we have the normal perpendicular reaction or compressive reaction at D as well as at E. And at E, okay, so the reaction at E is also perpendicular to this smooth bar, the axis of the smooth bar, and it is pointing towards the point of contact because it is a compressive force. Now, as I said, you have to treat this body as your body so that you can feel if the reaction at the contact point is tension or compression. So it is compression definitely, and it is directed towards the center of the cylinder or lug. Then if we draw the free body diagram of the lug, by the way, for the external reactions, the direction of the external reactions will not change. Only the internal reaction will change from axiom number 4. So because NE is an internal reaction, remember action and reaction forces are equal but oppositely directed. So if it is up to the left here, to the next body, it is down to the right. However, for the external reaction forces, they remain the same directions. Then we have here tension force at B due to the rope or cable. So that's the free body diagram. What is missing here is if the dimensions are are given, then we also have to draw or label the dimensions.